Look at these black, bright gold, and vivid green raisins. These colors aren't just a matter of variety. They are the result of three specific and very different scientific paths. A fresh grape is effectively a tiny biological water balloon, with water making up roughly 80% of its total mass. To survive, the grape evolved a waxy, semi-permeable cuticle to trap moisture. Escaping water simply bounces off this boundary. Because of this trap, a grape at room temperature won't dehydrate. The trapped moisture stays locked inside, breeding microbial rot. Turning a grape into a raisin requires intervention. We must bypass that waxy skin, disrupt its internal biology, and force water to escape. In this sense, a raisin is rarely a natural accident. It is the result of actively overcoming a fruit's evolutionary defense mechanism. The oldest method for extracting that water is traditional sun drying. Grapes are laid out on massive field trays, baking under the open sky to create the standard black raisin. Over several weeks, sustained heat slowly overpowers the waxy cuticle, forcing the internal water to evaporate through the skin. This prolonged exposure to the sun triggers a chemical reaction. Grapes contain natural pigments called anthocyanins. As the fruit sits in the heat, these pigments react with oxygen, changing their molecular structure and turning the skin dark brown or black. This enzymatic browning also builds the caramelized flavor compounds that give the black raisin its distinct, rich taste. To extract the water while stopping that oxidation, preserving a bright golden color, the process shifts from agriculture to chemical engineering. Treating the grapes with sulfur dioxide gas introduces a powerful antioxidant that halts the browning process entirely. To avoid the sun's heat, these sulfur-treated grapes are moved into mechanical ovens. This accelerates evaporation, locking in a soft texture and preserving the golden hue. In the raisin world, color acts as a visual timestamp. It tells you whether oxidation ran its natural course or if it was chemically halted. Long green Kashmiri raisins require a different approach. To preserve their green chlorophyll, these grapes must be kept completely out of the sun and dried in the shade. Shade drying introduces a thermodynamic problem. Without direct solar heat or mechanical ovens, evaporation happens so slowly that the grape will rot before it ever dries out. To speed the process in the shade, producers use accelerators. They either use the Objosh method, a microsecond plunge into boiling water, or they submerge the grapes in an alkaline solution of potassium carbonate and ethyl oleate. Both of these techniques physically bypass the grape's defense. The sudden shock creates dozens of microscopic web-like fractures across the waxy cuticle. These tiny cracks act as thermodynamic escape vents. They allow moisture to escape quickly, even in the cool shade. Whether baked in the sun, roasted in an oven, or hung in the shade, all of these methods share a strict universal target. They must drop the internal water volume to a precise 13 to 16% moisture content. Hitting that exact window is the threshold between breeding a microbe colony and creating a shelf-stable food. Removing over 60% of the fruit's water mass triggers the law of concentration, packing the remaining elements into a far tighter space. Without water diluting the internal structure, dietary fibers and sugars hypercondense. The particles pack tightly together, making the raisin energy-dense. This compaction causes a sharp increase in mineral concentration, specifically spiking potassium and iron far beyond a fresh grape. The specific dehydration method used dictates the final nutritional trade-off. Enduring natural sun exposure, traditional black raisins retain the highest levels of iron and antioxidants. This sensory analysis chart maps attributes across white-seeded raisin varieties to show how processing alters the final product. Golden raisins offer a sweeter bite, but sacrifice antioxidants to sulfur dioxide. Food science uses these exact profiles to determine a raisin's market acceptability. The next time you look at a box of raisins, you aren't just seeing shriveled fruit. You are looking at the intersection of thermodynamics, chemical preservation, and cellular engineering.